This video is for class 8 physics and we are doing spherical mirrors. From now onwards, in this chapter we shall talk about reflection of light, not refraction of light. So we are talking about reflection now. Okay, we have finished refraction. So in the reflection part we are learning about spherical mirrors, right? So let us understand what spherical mirrors actually are. So spherical mirrors are made by silvering. Silvering here means making one side opaque of a transparent object. Okay, of a transparent object we are making one side opaque by painting it with a silver color, and that process is known as silvering. Here they are saying we are silvering the part AB of the hollow glass sphere. So here they are telling us hollow glass sphere. So hollow glass sphere means we are taking a transparent sphere, okay, which should be hollow from inside like a football made out of glass, as shown in the figure 5.17 here, this figure. So here the silvering can be done in two ways. Okay, either we can make the glass opaque from outside like done here. So silver surface makes the glass opaque, right, thus creating a concave mirror such that its reflecting surface will be this. So that means if any light ray strikes this surface will get reflected, right? So thus this surface becomes the reflecting surface, and this shaded surface becomes the opaque surface because we have silvered the surface, or we have painted the surface with the silver color. Or the silvering can be done on the other side of the sphere also, right, that is from inside after cutting it. Then this surface will act as opaque surface, and this surface, this outer surface, right, will act as reflecting surface such that if any ray strikes the surface should get reflected. Okay, thus creating two kinds of mirrors. The first one, as you all know, creates a concave mirror. The second one creates a convex mirror. That means if the reflecting part is the bulging part, then it becomes a convex, whereas if the reflecting part is the inner curve, then it becomes concave, right? So let us go in detail a bit. The surface on which the silvering is done is called the silver surface, and the reflection of light takes place from the other surface which is called the reflecting surface. Okay, I hope we have understood till here. Let us go to the next topic, which is kinds of spherical mirror. So coming to the topic kinds of spherical mirror, there are two kinds of spherical mirror which we have discussed, and they are concave mirror and convex mirror, depending upon on which part you are silvering on a hollow sphere. Now concave mirror, a concave mirror is made by silvering on the outer surface of hollow sphere such that the reflecting surface or the reflection takes place from the inside the hollow or concave surface, as shown in the figure 5.18a. And convex mirror, a convex mirror is made by silvering on the inner surface such that the reflection takes place from the outer convex or the bulged surface, as shown in the figure 5.18b. So here are the figures for convex and concave mirror, right? So this one is your concave mirror, the first one, because the silvering is done on the outer surface and the reflection takes place from the inner surface. And this one here is the convex mirror because the reflection takes place from the bulging surface, whereas the inner surface is silvered, thus making it opaque. So I hope you have understood till here. Then we can proceed to the next topic, which is some terms related to the spherical mirror. Some terms related to the spherical mirror. Now the first term is the pole. The pole is the geometrical center of the sphere surface of the mirror. Okay, it's called the pole of the mirror. It is the midpoint of the aperture AB of the mirror. It is represented by the symbol P, that is shown in the figure 5.19. So let us go to the figure 5.19 and check the pole out. Okay, So, we have come to the figure 5.19 where pole is shown with the letter capital P, right. If we draw the mirror in this particular fashion, right, such that the rays are coming from your left hand side to the right hand side, then the center, the geometrical center of the mirror, okay, the geometrical center of the mirror is called the pole of the mirror. So, aperture means the curved portion here, right. Let us see in reality, if we take a concave mirror, where will the pole be? So, this is a concave mirror which I have taken, right. The pole of the mirror will in reality lie at the center of the aperture. So, this is the center of the aperture, right, and it is denoted by capital P, but we are not looking the mirror in this particular fashion when we are drawing the ray diagrams, right. In fact, the mirror is kept in this particular fashion, okay, in this particular fashion, such that the boundary of the mirror is facing you, okay, and the reflection is taking place from here. The light strikes here and the reflection is taking, right. So, sorry, it should be bended inwards, okay, right. The reflection is taking in this fashion. So, I hope you have understood where does the pole lie, okay, and this particular mirror must be made out of a big hollow sphere, right. So, let us go back to our book. So, after understanding the pole of the mirror, of the concave mirror and convex mirror, okay, I could not show you convex mirror, okay, because I do not have one right now. So, convex mirror actually is the mirror which is used as a rear view mirror in your vehicles, okay, that is convex mirror, okay. Spoon probably I can show, right. So, let us go to the next one, which is center of curvature. The center of curvature of a mirror is the center of the sphere of which the mirror is a part. So, it is represented by the symbol capital C in the shown in the again in the figure 5.19. So, actually this center of curvature is the center of the hollow sphere which was taken to make the mirrors, right. So, let us see. So, here is the diagram or the figure number 5.19. So, this part here, as you can see, this mirror is been carved out from this particular hollow sphere, and this particular mirror has been carved out from this hollow sphere. So, this sphere needs to have a center, this sphere needs to have a center, and that center is known as the center of curvature. The center is known as the center of curvature. Now, let us go to the next term, okay. Okay, there is a note also. The normal at any point on the mirror passes through the center of curvature. In other words, a line joining the center of curvature to any point of mirror is normal on the mirror at that point, okay. So, let us understand what normal is. A normal means any line drawn perpendicular to the surface. For example, if I have a flat surface, if I draw a perpendicular line on it, then this particular line becomes normal, right, and this particular line becomes normal. But here, since the surface is curved, okay, and any line drawn on the surface cannot any line which is drawn on the surface cannot be taken as normal, okay, but any line, if it passes through the center of curvature and touches the surface of the mirror, then this particular line will be making 90 degree with the surface. Thus, this line can be considered as normal, okay, can be considered as normal, okay. That is what the note wants to tell us. So, I hope you have understood this. We shall discuss this more when we are drawing the ray diagrams, okay, for the spherical mirrors. Now, the next topic or the next term which is related to the spherical mirror will be the radius of curvature. The radius of curvature of a mirror is the radius of the sphere of which the mirror is a part. Thus, it is the distance of the center of curvature from any point on the surface of the mirror. So, this is represented by the symbol capital R. Here, I hope you know what radius is. So, any line joining the center of the circle and the circumference of the circle, okay, any point on the circumference of a circle is considered to be radius, right, is considered to be radius, sorry, right, particularly this line here, this line, and this line is called radius. Now to make it simple, as our mirror is lying here, this is just the part which is not visible to us, okay. So thus we can take this line for our simplicity, this particular line from center of curvature to the pole. So I can define the radius of curvature, which is shown by capital R, as the distance between the between the center of curvature and pole. I can write here also, and pole, right. I hope this is clear. So radius of curvature is the distance between the center of curvature and the pole. So both the mirrors will have that three things which we have discussed, which are pole, right, this is the geometrical center, then the center of curvature is the center of the sphere from which the mirror was made, and the radius of curvature R is the distance between the pole and the center of curvature for a given spherical mirror. Okay, I hope these things are clear till now. Now going to the fourth point, which is the principal axis. So it is a straight line, this is an imaginary line, okay, it is a straight line joining the pole of the mirror to its center of curvature. Now the radius of curvature can be drawn anywhere from the center. For example, if I draw a line from this point to this point here, this will also be considered as the radius of curvature, but there is only one line which joins the pole and the center of curvature, right. This particular line which joins the pole and the center of curvature is known as the principal axis, P-R-I-N-C-I-P-A-L, okay, this one, principal axis, okay. The main, principal means main, right, axis means line, so main line, right. So the radius can be anywhere, but there is only one principal axis, okay. And what is the difference between radius of curvature and principal axis? Radius of curvature is the distance, okay, radius of curvature is the distance, whereas principal axis is a line. That is the difference between the radius of curvature and the principal axis. So I hope you have understood till here, right. So now going to the next term, actually this is also a term, okay, which is focus and focal length. Focus and focal length. In class 7 we have learned about the reflection of light at a plane mirror. When a ray of light is reflected from a plane mirror, it obeys the two laws of reflection, which were the angle of incidence is equal to the angle of reflection, and the incident ray, the reflected ray, and the normal all lie in the same plane. So this was studied in class 7, okay. If you have forgotten it, let us take few seconds to understand it. So suppose I consider a mirror, a line, okay, such that one ray called incident ray strikes the mirror or the surface, right. And obviously you will know that if this surface is opaque, then it will get reflected, and this line will be known as the reflected ray. So this is the incident ray, this is the reflected ray, right. And if I happen to draw one perpendicular line in between them such that it touches the point of incidence, now this point here where the incident ray strikes is known as, if you haven't seen, let me change the color, okay. Suppose the incident ray had strikes here, then that point will be known as the point of incidence. So this becomes our normal, okay. So I hope you have understood till here. Okay. Now there is an angle in between, there will be an angle in between the normal and the incident ray, and that is known as the angle of incidence, and there shall be one angle between normal and the reflected ray, that will be known as the angle of reflection. So according to the laws of reflection, the first one says that angle of incidence is equal to the angle of reflection. If this is 10 degree, this also should be 10 degree only, right. And the second law says that it is in statement, so I am not writing it in the mathematical form. So the incident ray, the reflected ray and the normal all lie at the same plane. That same plane means on the screen, right, they all are lying on the screen, the same plane at the point of incidence. Okay. So this were the two laws which we studied in class 7. So this is a slight revision, but our main topic is to understand focus. So whatever the laws are that we have studied, okay, whatever the laws are and that we have studied also is applicable for the spherical mirrors also, right, is also applicable for the spherical mirrors, right. So the above laws of reflection of light hold for the spherical mirrors as well. So let us go to the main topic again, the focus, right. Figure 5.20 shows the rays of light falling on the spherical mirror parallel to the principal axis. These rays are reflected by the mirror obeying the laws of reflection, that is the angle of incidence should be equal to the angle of reflection. The normal at the point of incidence is obtained by joining these lines to the center of curvature, because in the note portion we had studied that any line coming from the center of curvature and striking the surface of the mirror becomes the normal. So the reflected rays are not parallel to each other, but they are converging towards a point in a concave mirror while diverging from a point in a convex mirror. So in case of a concave mirror, the reflected rays meet at a point F on the principal axis. This point is called the focus of the concave mirror. In case of convex mirror, the reflected rays do not meet at a point, but they appear to come from a point F on the principal axis behind the mirror. So this point is called the focus of a convex mirror. So here are the figures, I shall explain with the help of this figure only, right. Let me explain for the focus of concave mirror. So this is the concave mirror, right. So here suppose the rays are coming such a way that it is parallel to the principal axis. When the rays come, okay, it strikes the mirror at this point and then will get reflected by obeying the laws of reflection, which is the angle of incidence will be equal to the angle of reflection. So when this ray passes, okay, or reflects, it passes through a point on the principal axis, okay, such that any other ray which is parallel to the principal axis will pass through the same point only every time, whatever the number of rays. If this line is parallel to the principal axis, this line, it has to pass through this particular point, right. So this point here on the principal axis is given a special name called focus, sorry, right, is given a special name called focus. Now see here, what you can observe is these rays here, they are being converged to a point, right, they are all the rays are coming and meeting at a point, so they are converging, right. So therefore this mirror is given another name known as converging mirror, converging mirror, okay, this mirror is given the name as converging mirror. So the other mirror, which is the convex mirror, right, it cannot converge the light, right, because the reflecting part is the bulging part which is outside. So any ray parallel to the principal axis, this is the principal axis, any ray parallel to the principal axis, when it strikes the mirror, right, it will follow the laws of reflection. Thus the rays of light will diverge, that means go away from each other, they will diverge, right. So but this ray, when I produce it backwards, they appear to meet at the they appear to come from this point here on the principal axis. So, this point here becomes focus for convex mirror, this point here becomes focus for convex mirror, right. So, I hope you have understood focus. Okay, the focus are different for convex mirror and concave mirror, right. Now, here you can see the rays are diverging, the going away from each other. Therefore, the name of this particular mirror, okay, is also diverging mirror, diverging, diverging mirror, right. So, we have two kinds of mirror, concave and convex, whose other names are converging and diverging respectively. So, I hope you have understood focus also, but there is something called focal length written, right. There is something called focal length written on both the diagrams. Actually, this focal length is the distance between the focus and the pole, like the radius of curvature was the distance between the radius the center of curvature and the pole. So, here focal length is the distance between the, so this is the focal length, okay, the distance between the focus and the pole. So, this becomes a focal length. I hope you have understood focal length also, right. I hope you have understood focal length also. So, this applies for convex mirror also, right. The distance between this focus and the principal axis, focus and the pole, focus and the pole, not the principal axis, okay, I am so sorry, it is between the focus and the pole. So, this line is known as focal length, okay, distance. So, this distance is known as focal length. So, I hope you have understood till the terms related to this particular spherical mirrors about focus and focal length, etc. Okay. So, now we can go to one activity, which is activity number 5, right. Just before this, when I was explaining focus and focal length, okay, we had taken the rays parallel to the principal axis. The principal axis is supposed to be here, right, but it is not necessary that the principal axis the rays will be always parallel to the principal axis, it might not be. So, under that circumstances, okay, if the rays are in this particular fashion shown in the figure, right, then also, okay, we can take out the focus, okay, with the help of this particular activity you will understand how. So, take a concave mirror and hold it such that it faces the sun. Now, place a piece of paper in front of it and adjust its distance from the mirror such that at one position a very small image of sun is seen on the paper. You will notice that the paper charge at this point, that means starts catching fire, okay. This point is the focus of the concave mirror. So, measure the distance f of this point from the mirror with the meter rule. This distance f gives us the approximate focal length of a concave mirror. It gives us the approximate focal length of a concave mirror. So, now there is one relationship between focal length and the radius of curvature, which I need to discuss, okay, before going to the next topic. Okay, let us go to that particular so paragraph, coming to that paragraph, right. So, focal length, here they are written, focal length is always equal to, focal length, that small f, right, is always equal to half of the radius of curvature, or I can write focal length is equal to radius of curvature upon 2. If we have a radius of curvature 4 centimeter, then the focal length of that particular mirror will be 4 divided by 2, which will be 2 centimeter. If the radius of curvature is 10 centimeter, then the focal length will be 5 centimeter, and so on. So, I hope you have understood, okay, this much for this video. Thank you so much.